So I'd like to hand over to George to give an introduction on Odyssey.
Well, good morning. It's an honor to be here, and it's very fun to be here and to talk about Odyssey. This is the second annual symposium, but I point out that Europe has been very involved in Odyssey since its beginning in 2014, and collaborators have been involved in its predecessor, OMOP. So Europe is not new to this, but it's great to have Europe's own personal presence in it. So my name is George Ripsack. I'm chair of biomedical informatics at Columbia University, where we hold the coordinating center for Odyssey, which means that when there are bills to be paid, I worry about it, collecting the money to pay them and then paying them. And other than that, the work actually occurs distributed around the world. So what I'm going to do today is two things. One, introduce Odyssey for those who haven't been here, so there'll be a review for many of you in the audience, but it'll be new to some of you. And then go over, I think it was going to do a year in review. I thought I'd focus on the one, spend more time on one particular project we're very excited about related to hypertension, and that's where I'll put a lot of my time. So first of all, our mission is to improve health by empowering the community to generate evidence. So generate evidence is something I'm going to be saying repeatedly to promote better decisions and better care. Here's our network, and you can see we're spread around the world. In US, Europe, Asia. That's where we have our database. We have collaborators around all around the world, almost 7 continents. We had 7 continents, but the person had just left Antarctica, and his successor never answered his email. So I was almost able to claim 7 continents, but lost it. So I have an atmospheric physicist friend who is going to find someone there so we can make that claim. We have 200 collaborators from 25 countries. And we have about 500 million unique patients. So that's not records, because that could be redundant records, but actually about 500 million unique patients are represented in our network today. And when I say generate evidence, there's different ways of cutting it. Here's one way, and 3 things. The first one is basically characterization, which is tallying, just counting things, not making a lot of inferences, just saying what can we directly see, and I'll give you an example of that. Second one is doing causality, so that's population level estimation. Does this drug in general cause this side effect, for example? And the last one is patient level prediction, where for individuals, will this drug affect me in particular, and what's my risk? We're an open science initiative, so there's open source software, but not just that. We share everything. We open about everything that we do when we do a study. What are all the hypotheses we tested? What's the code that we used? What was our random number seeds that we used in our code, et cetera. So try to be as open as possible so that our things can be duplicated. How do you collect data on 500 million patients around the world? Well, easy, you don't. The way you leave the data where it started, you do a federated approach. So everyone keeps their data locally, convert their data to the OMOP Common Data Model. We call it the OMOP Common Data Model because that was its original name. And we thought if we changed the name from OMOP to Odyssey, no one would adopt it. So we felt it was important, that branding. So we just kept the old name, even though we are fully the owners of that model. So you convert your data to the model. It does take work to do that. And then we disseminate the query around the world. It's a voluntary network. Whoever answers, sends back the evidence, and then we generate papers collaboratively. Everyone who donated data or time for the analytics or funding ends up being a co-author on that paper. So we're trying to follow the model of, say, CERN. Here's the data schema for our common data model. And it's basically organized to optimize research. If you had to create a database, a medical database that was going to do research on 100 million patients at a time, how would you organize that model? And that's what we've come up with. And here's a point, it's not specifically on a slide. Everything we do is driven by generating evidence. So there are other common data model efforts which are driven by the desire to represent the data fully. And that's a good thing to do if all you want to do is represent the data and store it. But if you actually want to do analytics on 100 million patients, then you got to think about some other issues like performance. And so when we do it, we want to get the representation right, but we also have to get the analytics to work on that at the scales that we're talking about. So what I like about Odyssey is that it's always driven by the goal, which is to improve health through generating evidence. Extended vocabularies, 100 different vocabularies that we pull from to translate all these data into a common set of standard vocabularies. Around the world, SNOMED for diagnoses, LOINC for measurements, ARCS-norm for medications. ARCS-norm is a good example where ARCS-norm, since it's largely US-driven, ARCS-norm doesn't include drugs that are not offered in the US. So what do? Odyssey creates ARCS-norm extensions. To add to ARCS-norm, we want to try to trick the US into adopting the world medications, and we're working on that still, but until then, we're doing it. So we are producing ARCS-norm for the non-US medications, for example. So we'll take on whatever is needed to get observational research done around the world. And then standardized conventions, and this is another example actually in the upper right corner, Odyssey adjusting to experience, again, driven by what goes wrong in real life. It's not just a theoretical data model. So over the last 30 years that I've been doing this, there's been these standards, HL7 version 2, which is a messaging standard, and if we could just move to HL7 version 2, then electronic health records could talk to each other. And then you do it, and in fact, there's nothing in common between the two messages you get between two different systems that both purport to use HL7 version 2. Same thing happens as you go forward. FHIR's may be a little bit more detailed more recently, but bottom line is there are so many decisions. Even once you pick a schema and a vocabulary and some other things, you still end up with local interpretations of how to use that thing. So these standardized conventions for us to be explicit about the assumptions we're making so that when we share data, we all share it in the same way. And it's an empirically driven process. That is that we, as we go along, that's why this thing follows the other two. As we go along and see what doesn't match, we know that we need schemas for that. We supply tools for you to help you do your data conversion. So a lot of the work in Odyssey is in building these tools collaboratively through open source software. So here's a set of tools to prepare your data. And we supply tools to curate your data to make sure that you achieve the data quality. This is a set of consistency checks. And then tools to do the analysis, to build, visualize, and analyze cohorts. And I'll show you some examples there. And then to characterize those cohorts and visualize the results. So I won't go into details on the tools today, but those are a lot of what Odyssey supplies and kind of refer to as the Odyssey stack and Atlas you'll hear us talk about. So now let me show you some examples of Odyssey in action. So the first example is a study we published a couple years ago. It was our first large-scale study. I'll just go through it quickly because I want to get to the next one. So this is an example of characterization. So it's one that you can't argue with us too much about it. We may have some measurement error here or there, but we're not asserting causality. We're not worried about confounders. And so it's something we can publish and say, here's what we observed. And the topic was treatment pathways. Basically, how does a patient end up with a particular drug versus another drug? Well, it's actually fairly complex if you go through the full influence diagram of how a patient and doctor come together to make a decision about a medication. And so given that, as you look around the world or around practices within the same country, there's going to be a lot of variation. And if I ask you, how do people treat diabetes, I can tell you what the guidelines are. And maybe there's a couple of papers that in a minor way say what's happening at an academic medical center, but it's not well characterized how diseases are treated around the world currently. So we had the idea to do this study at the American Medical Informatics Association meeting in November of 2014. And so we had the idea, literally just said, okay, let's try this. And within 3 weeks, December 5th, we had the results from a worldwide study from 7 of 12 sites that eventually did the study. So it took only 3 weeks to go from the initial idea to building the code for that study, executing it, collecting the results centrally. We actually ended up with 12 sites agreeing. Remember, it's a voluntary network, so not every site necessarily agrees to do every study, but here are the ones we did. from Korea, from US, from UK, from Japan, from Hong Kong. Did I miss one? No, I think that's right. It was about 240 million patient records. There's some duplication there, so the actual number of unique patients may have been a little bit smaller, but 240 million patient records in that study. We published it in PNAS, and as you can see, it's a large author list of everyone who was contributing to that study. And here are the results. Again, this is the only slide I'll have on this, but just to review it, what these are, these sunburst diagrams, the inner circle is the first drug, then the second drug, and the third drug, and so far out. The left column is diabetes type 2, second column is hypertension, third column is depression. We see a lot of agreement on diabetes. Most nations start on metformin. 75% of the time, patients start on metformin. Hypertension, you see some agreement, a lot of hydrochlorothiazide and lisinopril, but not as much as diabetes. And for depression on the right, we see the least agreement, where it's as if you spun a wheel and it's a random selection of drugs, which makes sense clinically because we don't really know which drugs are best for which patient in depression, but for diabetes, we do have guidelines. And then we see on the lower right that Japan was, and I'm only showing 3 of 12 databases, but if you look at 11 databases, all look the same. 75% or 60 to 75% metformin. Japan was only 25% metformin, even though Korea and Hong Kong were also like the US, UK, et cetera. And so we assumed it was a formulary issue that the government wasn't paying for it or something, or there was a substitute drug. But when a Japanese diabetes physiologist happened to be visiting Colombia a couple of weeks later, she said that, in fact, Japanese doctors believe that Japanese patients don't get as much insulin resistance. They're genetically different and don't get that. And so they tend not to use metformin and tend to use other drugs. So I searched the literature then. I already searched the literature and couldn't find it. But on my search, I found 3 papers that mentioned in a sentence or two that they thought there was less insulin resistance. I don't know if it's true, but it's thought to be true, and it has influenced prescribing patterns. But what do we conclude from this, not from the medical view, from the Odyssey view? Well, first of all, we had by that point encoded, let's say right now, we're at 500 million unique patients, about 2 billion records, but there's duplication. If you can voluntarily encode, 700 million records, then you've just encoded 1/10 of the world population in a voluntary basis. And I think if you can do 1/10 of something, you can do the whole thing. Now, of course, the first billion are the easy billion, and the last 6 billion are the harder 6 billion. So I admit that, but still, it's a pretty good achievement. So generating evidence is feasible. The stakeholders were willing to share and participate in these studies, and we were able to accommodate vast differences in privacy and research regulation because we have a federated approach and keep the data local. Which then spurred us, and this is available online at howoften.org, which just links to the Odyssey site, but we wanted to do something that was easy to remember. And this is an example of characterization. So this is not attributable risk, but absolute risk. But for any drug on the world market, for any side effect defined in SNOMED, so 200,000 terms, what is the rate, what is the incidence of that side effect in that drug? So given a side effect, what proportion of the time of patients who didn't have that side effect before they started the drug, how many had that side effect afterwards? What you really want to know is did the drug cause it? Because, for example, statins have a high incidence of heart attacks. The statins didn't cause the heart attack. They were ordered because the patient was already at a high risk. So this is what I mean by absolute instead of attributable risk. But if the risk is low, that includes the attributable risk. So if it's low, you're probably safe. So when I get a new drug or a family member, I actually go on here and just look and see what the incidence rate of different side effects are out of curiosity. And the user interface isn't great yet. It's just, you have to use the generic name. But it is a nice website, and we see that growing over time. We were hoping that Google would take it over and had Rob Califf working on that, but he got busy doing other things so far. So we'll see. We'll work on that again. One thing, like as I go through the US, for example, a lot of people see Odyssey as just the other name that I can't remember for OMOP, which is a data model. And so should I use the OMOP data model or I2B2, or should I use Sentinel, or should I use one of a couple of other data models? But Odyssey is not just a data model. We're an open science effort, and the data model is driven by science. And I think that's a key differentiation from this effort, from those others. Or should I use FHIR? And I don't want to get into the discussion of how FHIR relates to a research database, and it's a messaging standard, and yes, there are profiles, so that we could go have that as a separate discussion. But the important thing is that Odyssey is not just a data model, so we do methods development. Why do we need to develop new methods in observational research? Well, some of you have said, I think I probably showed this last year, but so there's a paper in JAMA, so it's an OK journal, and BMJ, which is also an OK journal. So two pretty good journals. And if let's say we have a question, how often do bisphosphonates cause esophageal cancer? Let's pick a database like the General Practice Research database from the UK, and let's answer that question. Okay, two groups set out, two groups given their answers a month apart, and one says yes and one says no. So when the lay public reads this, they just don't know what to do with it because one is saying yes and one says no. So one doesn't have enough power. Like they're not going in opposite directions, but one's saying yes and one's saying there's not enough power. And it is on the same database, so they should have probably come up with the same answer. And as you know, when you read the newspapers, this year coffee causes cancer, and the next year coffee cures cancer, and then it goes back and forth every other year. So what's going on? Well, that's what we set out to look at. This diagram is a cheat sheet, so you'll understand the following slide. So on this, we're mapping the effect size, where a 1 means there's no effect, that's an odds ratio of 1. To the right means that a drug causes a side effect. To the left means, whoops, oh, it may accidentally be on a timer. And the left means it stops the side effect, and on the top means not statistically significant, and that dashed line is a p equals 0.05. If you parse the literature and you plot every 30,000 studies on this graph, this is what you get. So what we see is a lot of publications saying it shows a side effect, fewer saying it's protective of a side effect, that is, it has a good effect, and a dearth of studies that says it has no effect. 85% of published observational studies are positive. So what does that mean? It means we have a lot of publication bias, because if you look along 0.05, which are those dashed lines, there's a sharp demarcation. So we're not guessing well, because otherwise we're guessing that p equals 0.051. I'm not going to bother with that one, but p equals 0.049. Yeah, that's a good one for me to do. So it's happening after we do the analyses. And it also shows p-value hacking, which I don't have time to go into. So we have a problem where we're not publishing everything, and we have a lot of bias in the literature. So what does Odyssey do to address bias? So I'm going to go through 5 things that we do, and the ones in red are the ones that are pretty much unique to Odyssey. First, we do propensity score adjustment for confounding, which a lot of people do. It's become the standard. We do it in a systematic way on all the variables. So we do large-scale adjustment. So we take all the variables and we use lasso to pick out the ones that are relevant, which then for us creates balance that we don't see in other observational studies that are also using propensity score stratification. Again, not enough time to go through each of these. Confidence interval calibration. We take a bunch of negative, it's becoming popular now to use negative controls when you do observational research. Well, we do like 75 or 100 negative controls to see if, when we do our study design, do we generate a lot of false positive results? And we calibrate our confidence intervals based on those results. We use multiple databases around the world, different locations, practice types, excuse me. And as I mentioned earlier, we publish all hypotheses, code, parameters, and runs. That's the random number link. And we do it at scale so we can ascertain our performance characteristics at a large scale. So we do a number of things to create reproducible studies. And when we do this, now this is a study of depression. I'm going to show you a different example in a moment. We see that we produce a plot that is not missing the middle, that doesn't have p-value hacking. 11% are positive, which means about 6% are true positives because 5% are false positives by the definition of a confidence interval. And then we actually generate evidence. We don't just study methods. So about a year ago, the US came out with a guideline for hypertension. The EU came out with one more recently, I guess in the fall. The way these guidelines are written, there are recommendations for hypertension treatment, and they're rated on the evidence. So what you want to do is have strong evidence for your recommendations, which usually come from, say, a summary, a meta-analysis of randomized clinical trials. I'll go back to that point in a moment. Here's the US guideline. There are 5 classes of drugs that were selected as first-line treatments. Those 5 classes have 29 drugs in total, and then there are second-line treatments, which have 28 more drugs. So this guideline isn't very specific, basically 28 different drugs. So you say, how should I treat hypertension? Patient is sitting in the doctor's office, and you have one from 28 to choose from, without a lot of selection within there. These guidelines were generated based on 40 randomized trials. And what's shown here is a picture of all the different drugs in the first line with classes and subclasses within there. Actually, this is first and secondary class drugs. And those are all and every link there is a randomized trial that compared 2 drugs, so the comparative effectiveness research. What you'll find there is there are like half the drugs have never had a clinical trial saying what you should do with it. So how can the guideline assert that this is a first-line drug that you should use for your patient when there's never been a randomized trial? Well, because they made an assertion that, well, it's within the same class, it probably acts the same way. Well, that's expert opinion. If I go back up to here, in fact, yes, they made an assertion about a class, and that may be green, which means strong evidence. But if you go down to the individual drugs, it's not green, it's some other color, like, I don't know, I forget what the colors are, but yellow or red or something, which means it was someone's opinion that we should include those together based on my beliefs about physiology, but there was never actually a study that showed it. So Odyssey said, why don't we fill in this chart and try to generate the evidence so that we can actually draw conclusions. Now, it's observational evidence, so we have to handle confounding, but it's better than expert opinion, which is just a belief that this thing should be included like that. I'm going to go through this. So here's the evidence for myocardial infarction, stroke, and heart failure. And what we see is among the first-line drugs plus beta blockers, there's not a lot of difference based on randomized trials. We see that beta blockers seem a little bit worse than ARBs, angiotensin receptor blockers. And in fact, the difference between the US guideline and the EU guideline is the US guideline says don't use beta blockers first, and the EU guideline allows it. So that would be a point. And then there's some other minor difference. So that's what the evidence shows, is there isn't much difference among them. So then Odyssey, when it set its study, it does it at large scale. So we picked 58, or now 50, depends on how you count, 58 to 55 outcomes of interest, both effectiveness, like does it do what it's supposed to do, and safety, does it cause effects that you weren't looking for? So the effectiveness would be, does it stop heart attacks? The safety would be, does it cause hyperkalemia? And then, as I mentioned, we do negative controls. We looked at other effects that we don't think are caused by hypertension drugs, and these were generated through literature review, looking at product labels and manual review. We do this across 9 databases shown here, which include both claims databases and electronic health databases, and they are databases from around the world, several from the US, but also around the world. So we're doing a study of all those drugs, 58 drugs, first and second line, and then all those outcomes on all those databases. If you do that, you get basically, so the full thing isn't there, but basically you get billions of studies. And we studied not just every drug, but every combination of drugs. So we're comparing every combination drug, so every 2 drugs to every other 2 drugs. So that's 58 to the 4th power, times another 58, because that's how many outcomes we have. So there's a lot of studies, but about 500,000 of them, shown in the lower right corner, is the number of studies we were able to do. There are results in that diagram. That just shows that we didn't have publication bias. When we do these studies, Odyssey is very much about reproducibility. So we make sure that our results are pass all the diagnostics. I'm going to show you two examples. So this is a set of hypotheses that we tested. This diagnostic is telling us that there are two drugs, and the two groups of patients who took those drugs that we compared are sufficiently similar. The purple, between the blue and the red, that purple is sufficient overlap that we can compare those two drugs using our methods of propensity score stratification. Whereas this one shows that the two groups are so different from each other that I can come up with a mathematical answer. I can do the arithmetic and come up with an answer. But when I look at this, I'd say I don't trust that answer, because even if we were able to balance these two, to match these two populations, it would mean I'm balancing on that tiny purple area, so they're probably very unusual patients. But my real point, stepping back, is that Odyssey takes the time to look at each of those 500,000 studies we did and say which ones do we trust and which ones don't we trust. So a lot of this is, it's not just throwing out 500,000 hypotheses, throwing it on the wall and seeing if it sticks, so to speak, but actually doing it in a thoughtful way. Here are some of our results, which show on the left is the randomized trial. So these are the first-line drugs and the second-line drug of beta blockers on that first slide on the left, and the RCTs not showing significant differences in the meta-analysis. And on the right-hand side shows our results, and those colors mean that we're beginning to see some differences specifically. So now green means a green square means that the drug on the left is better, and a purple square means the drug on the bottom is better. And so what we see there is that line of purple across, or the line of green up and down, says that beta blockers appear to be inferior to the other first-line drugs. It says that, the US guideline was probably right, and beta blockers should be seen as a second-line drug and used only for specific circumstances or if the other ones didn't work. And then we see a very specific result over there that thiazide diuretics are better than ACE inhibitors. ACE inhibitors are the most common single class used. If there's something better than that, half the patients starting on hypertension treatment in our study started on ACE inhibitors, and we're finding there's something better than that. That's a big result. A lot of people have hypertension around the world, and if half the doctors are starting people on ACE inhibitors and there's something better than that, this is an important result. In fact, I think it was better both on safety and efficacy, right? So it was better effects and worse safety for ACE inhibitors than thiazide diuretics, believe it or not. Here's our overall result showing by drug. I'm getting near the end of my slides here. So there's 4 corners there, 4 squares there, okay? The first-line drugs in the US guideline are in the upper are the first half, and the second-line drugs are the second half. So if the US guideline is right, what we should see is gray in the upper left corner for the most part, because that means that the drugs are all equivalent. And in the upper right, we should see green because the first-line drugs are better. In the lower left, we should see purple because that's just saying the same thing, that the first-line drugs are better. And on the lower right, we should see a mix of green and purple, green and violet, because they're second-line drugs. We don't know which ones are better than the other. And in fact, we pretty much verify the US guideline that it more or less got it right, that according to our analysis, we're in pretty much agreement. The one that's off is captopril, but actually didn't pass the diagnosis. It probably is an inferior drug, but we can't claim it because it didn't pass its diagnostics. Captopril is an older drug, and it's a non-dihydropyridine calcium channel blocker. Now, how did we do on evidence? So on the left is the diagram I showed you earlier of what the randomized trials show. On the right are all the hypotheses we were able to test. The point being that we filled in the blanks. So the difference between those two was expert opinion in the US guideline. And now we've turned expert opinion at least to observational evidence. Observational evidence that's doing the most modern methods of adjusting for confounding, and that is run over a large number of databases around the world, so good generalizability. Those randomized trials are each done in a specific location usually. Our evidence is generated around the world, so you can argue it's better generalizability than the randomized data. So what do we find clinically that, I guess I went through them already, that beta blockers really are inferior, that thiazide diuretics are better than the ACE inhibitors. We also not shown here, we found the US guideline says you should start on 2 drugs. Don't just give 1 drug, give 2 drugs, because you want to do tight control. And in fact, we found that the converse, that, and it could be that giving 2 drugs is safer because you give a lower dose of each one, so you have a less chance of a side effect, but we didn't find that. Instead we found the opposite, which is that if you give 2 drugs, you have twice the chance of the side effects because they have complementary side effects. So we found worse safety, and I think the same efficacy. Same efficacy, but worse safety if you start on 2 drugs instead of 1 drug. And I won't go through that bottom one. So this is my last slide. But before I go to that one, we're very excited about this study. We're writing the papers right now. We're looking to go to good journals. We think that the implications are very strong. Could have an effect if half the prescriptions written for new hypertension treatments, shift because of this result. That would have a huge worldwide effect. And it's something that other groups haven't been able to take on. So, when you use our data model, we don't just want you to use the data model. We want you to join the network and participate in this research and be co-author on these papers. So it is feasible to create an enormous international research effort. We found that sites do volunteer to run studies. We're completely open. We're taking a concrete approach to address the credibility crisis, that is to improve the reproducibility of studies. And we may not have it all right. The way we do our propensity score matching maybe can improve someday. The way we're using negative controls may improve someday. But the point is we have an infrastructure in place that we can do the research to figure, like right now, when you run a study and publish it, you have 1 study. You can't tell no one can tell if you did a good job or not. They just have to trust you. They have to look at your CV and say, yeah, you wrote a lot of studies in the past. Maybe this is a good one too. When we publish a study, you can look at our operating characteristics. You can look at a number of results and say, does this make sense to me? So we can measure operating characteristics. We can study reproducibility, and therefore then we can improve it. So I think we have something special. And just the final point, which I already made earlier, that Odyssey supports all parts of the evidence generation process, and not just the data model, and actually not just the methods, but generates evidence. And that's what we're all here for.